Welcome you all to the next lecture on the inorganic complexes, or primarily the coordination chemistry aspects pertinent to this particular course, which is inorganic chemistry of life. In the previous class we have looked at various characteristics of the coordination complexes in terms of the ligands, and towards the end I talked to you about spectrochemical series and the effect of the ligands on the splitting energy. So, the halides split to the least compared to the oxo ligands, compared to the nitrogen ligands, compared to the carbon ligands. I also mentioned to you that these can be explained not by the electronegativity principle, but by their pi acid pi base characteristics. Now, so at this juncture let me introduce what is the acid and base mean by. So, the metal ion is considered as a Lewis acid, and the ligand is considered as Lewis base. Okay. So, what is Lewis acid and what is Lewis base? So, I am sure every one of you know that what is a Lewis acid, what is a Lewis base, but nevertheless to bring to a recapitulation, then let me tell you that the Lewis acid is the one where you will find a low lying empty orbital, means an orbital which is empty, which is ready to accept electron pair. On the other hand, Lewis base is the one where you have a filled electron or electron pair which is higher energy, therefore is ready to donate. So, ready to donate, ready to accept. So, accepting is coming to the Lewis acid, donating is coming to the Lewis base character of this. This is an important concept that you need to keep in mind when we are looking at. All the metal ions are Lewis acids and all the ligands are Lewis bases. So, the ligands coming from, for example, in the biological systems, what are the ligands? We have seen the carboxylate group is a ligand, a thiol function is a ligand, a phenolate function is a ligand, an amine function is a ligand. So, all these kinds of ligands are all the Lewis bases. And the metal ions, of course, we have the iron 2 plus, iron 3 plus, or copper 2 plus, or zinc 2 plus, nickel 2 plus, manganese 2 plus, all of these. So, therefore, this should be clear to you when you are studying the inorganic chemistry of life or biological inorganic chemistry aspects. So, therefore, I have introduced this concept. Please do a bit of exercise so that you get familiarized with these by looking at some of the examples of these. Okay, what I explained to you earlier, the halides the weakest in terms of splitting the energy, and the carbon ligands like cyanide and carbon monoxide are the strongest to split the binding energy, and therefore, the ones which split large will try to impose pairing of the electrons, whereas those which split to less extent will not impose any pairing at all. So, therefore, you will have the high spin complexes coming from these ligands and low spin complexes coming from these ligands, okay? And that is one thing is good enough. Now, there is another aspect that we need to understand about the inorganic complexes or coordination complexes. So, the coordination complexes, inorganic complexes, what we need to know additionally is that the hard and soft character of both the Lewis acid as well as the Lewis base. Just now I have already defined to you Lewis acid as well as the Lewis base. So, to explain its hardness and softness, so we need to look at the following aspects. So, let me give a note of caution. This hardness and softness is not a mechanical hard and mechanical soft, it is a chemical hard and chemical soft aspects of that, which is dependent on the polarization as well as the polarizability. So, atom is the one which is having a nucleus and electronic cloud. So, if the electronic cloud is distorted a lot, okay, then the size of the ion will be increasing, and that becomes more softer in a chemically. Okay. And on the other hand, if you have a smaller size, smaller electron cloud, then you have a strong capturing by the nucleus. So, therefore, such kind of things will tend to be hard, chemically hard in nature. So, this means what is important is polarizability and polarization. See, when you take an ensemble of a molecule or an atoms, each atom or each molecule is in the field of all the other molecules. So, what field? Electric field of all that. So, therefore, this electric field try to distort the electron density of the central one. So, if it is able to distort quite well, it's a its ability for the distortion is quite large, and that is referred as the polarizing ability of this. Polarizability, to what extent an atom can get polarized, an ion can get polarized, a molecule can get polarized by the surrounding electric field, which is generated by the neighboring atoms, neighboring ions, neighboring molecules. So, therefore, you can take it as a kind of a rule of thumb, small ions or small atoms, highly charged cations, they have a greater polarizing ability, but they will not get polarized. They will polarize others, they will not have their polarizing ability is more, but polarizability is low. Large and highly charged anions are easily polarized, and that means they get their polarizability is much greater on this. So, similarly, if you can look at higher ionization energy, small size, low polarizability, these are referred as harder. This is chemically harder. Those having a low ionization, larger size and high polarizability, they are softer. So, as I said, both the Lewis acids can be harder, Lewis acids can be softer. Similarly, Lewis base can be harder, Lewis base can be softer. And as I said, the metal is called the Lewis acid, ligand is called the Lewis base. Therefore, you are looking at the combination of Lewis acid and Lewis base. So, therefore, the hard acids will combine strongly with the hard bases, and soft acids will be combined with the soft bases. So, hard combination is stronger, soft combination is stronger. Generally, the lighter elements of a group, when you look at the periodic table, a group, they are chemically harder, and the ones which are down, which are heavier in that group, they are all softer in that kind of thing. So, same thing is explained by the diagram over here, which compares the polarizability with respect to the ionization. So, the ionization, polarizability, ionization and polarizability. So, the greater ionization potential with a lower polarizability, lower ionization potential with a greater ionizability, that is all the thing that we need to know. So, this can be further explained by using the homo-LUMO kind of a idea. See, the acid will have an empty orbital, and this is what you can look at, and the base have a filled one. So, so this becomes hard when you have a greater gap, okay? And so therefore, you can see that the hard base with the soft becomes, you need a lot of energy difference. A hard acid with a hard base does not require much of a energy variation. So, that means energy comparability or low lying orbit, the empty orbital and the fill orbital should have a comparable in their energies. If they have a comparability in their energy, of course, symmetry is also important, then you will have an easy overlap. So, therefore, the hard acid, hard base will have a better overlap, whereas hard base with a soft acid will not be so favorable. Okay? And similarly, soft acid with a soft base, there is a favorability. So, therefore, soft acid soft base combination is better because their empty orbital and fill orbital respectively are in parallel in reasonable energy comparison. In case of hard acid hard base, again the empty orbital and the filled electron pair have a comparable energies. All that you need to keep that in mind is. The second thing that you need to keep in mind is, if the HOMO to LUMO gap is large, then it is hard. If the HOMO to LUMO gap is smaller, then it is softer. So, harder and softer kind of a thing that you can look at. So, this can also be talked in a little different way. This is nothing but the difference in the ionization energy of a neutral atom and its anion. So, what is the ionization energy of the neutral atom? What is the ionization energy of its anion? That difference. If difference is large, then it is hard. If the difference is small, it is soft. Just like the homo-LUMO difference. Homo-LUMO difference is large, again hard. Homo-LUMO difference is small, it is soft. Okay. So, this can also be quantified by using the Pearson absolute hardness scale eta. So, I minus A by 2, okay, the HOMO energy and LUMO energy by 2. So, it is so hard acids tend to combine with hard bases preferentially, soft acids tend to combine with soft bases preferentially. Why? I just now explained to you. The reason is that the hard acid having a empty orbital and the hard base is having a filled orbital, these two orbitals have very comparable in energy. Similarly, soft acid having an empty orbital, soft base is having an empty or filled orbital, these two having very similar in energies. So, therefore, such kind of cases will give a more preferential binding. So, soft acid, soft base combination is stronger, hard acid, hard base combination is again stronger in the complexations. Okay. So, just to give an idea, as I said that the ions with a greater charge, smaller size will be tend to be hard, having the smaller charge and greater size obviously will be softer, and the anions more and more anionic charge will be softer, more and more cationic charge will be harder. So, just keeping that in mind, you can divide these into hard and soft with some kind of a borderline cases. As you can see, it's +1 sodium, lithium, potassium, magnesium, calcium, manganese, chromium, etc. Borderline you have is zinc, copper, 2 plus, nickel, etc. And softer copper plus, silver plus, gold plus, okay, thallium plus, they are all very large in size and smaller in charge. So, these for large in size and smaller in charge, they will be tend to be more softer, and those which greater charge and smaller size, even if the charge is smaller, the size is also smaller, then again hard. So, they are hard, soft. So, this is within the acids, and this part is within the bases or ligands or anions. So, this is the Lewis base and this is for the Lewis acid. So, you can see that oxygen based one, water, ROH, O minus, they are all on the hard side, these are all oxygen based ones. And then if you have a nitrogen based ones, they are somewhere in between or borderline or intermediate. Now, if you look at the sulfur based ones or carbon based ones, these are all softer, that we have seen already too. Okay. So, therefore, hard base, hard soft base, hard acid, soft acid. I hope this is clear to you. So, towards the end what you need to remember is the size and the charge. If the size is large and the charge is smaller, softer, size is small and charge is greater, again is harder, whether it is an anion or cation kind of thing. So, you need to look at both of these. Okay, so we have tried to finish quite a few aspects of this. Then how do we try to understand this into the metal ions into when you put them into biological systems or when you put into the biological systems like proteins and enzymes. So, what you look at there, one is that the metal ion sits in the metalloprotein or metalloenzyme and does not sit ideally, as I have shown you already, is bonded to the side chain residues of the protein and forms a coordination complex. So, it interacts, it binds, therefore, it is a thermodynamic stability is associated with this. And of course, the surrounding groups which are coming from the protein will also apply certain kind of criteria conditions on the metal ion in terms of the geometry and in terms of the crystal field splitting, other kinds of things. So, it all follows the coordination chemistry principles what you want. So, now what we saw is the situation where you have a metalloprotein, you have metal ion sitting in this, and that is not sufficient enough. That tells you about the only thermodynamic, but what you require is kinetics. And metalloenzymes are what? They are catalytic, they show reaction, they are not just like that sitting ideally there. So, therefore, the metal enzymes and metal proteins having a metal ion or metal complex inside the protein and the protein compartment, but they do show a function. To show a function, you need the reactivity, and this is the reactivity which we are talking about in terms of the lability aspect of it. So, this is absolutely important. Again, it depends on what is the kind of a coordination sphere that you have, what is the charge of the metal ion center, what is the size of the metal ion center, and what is the protein influence. All of these again influence the lability. All those parameters which are influencing the stability are also influencing the lability as well in a different way. So, one of the ways of understanding the lability is that suppose you have a coordination complex having a ligand bonded to the metal center. If such a ligand can be exchanged by an outer ligand or outer ion or outer molecule, and the rate at which it can be exchanged is the one which you can talk in terms of the lability or rate of exchange or rate of reactivity. So, all these things generally one would measure. You take a metal ion with a coordination sphere of water and you take a labeled water in the bulk and see how well a labeled water is exchanging with the water which is bound to the metal center, that kind of a rate. So, the greater the rate of exchange between the coordination sphere and the bulk is the kind of a rate of exchange that you can explain in this. So, the facile other kind of a things is redox. So, during the reactions, a large number of reactions in metal enzymes, the metal ion undergoes the redox, not necessarily in every case, but large number. So, metal ion can go oxidized, can undergo to reduction. So, redox process will happen. So, how well this redox process is favored by the protein or enzyme? They are still bound to the enzyme. Can the enzyme allow the next higher oxidation? Can the enzyme allow next lower oxidation state? So, if the enzyme can allow both of these, then you have a facile redox process in these things too. So, their capability to act as a Lewis acid to activate the how well they will activate the organic moiety. In this case, organic moiety is the protein, and organic moiety is the small molecule which comes and binds to the metal center for activation or for recognition purpose. All of these are important in the physical aspects of that. So, we have looked at the stability, we have looked at the lability. So, let us look at the stability aspect with a little more quantitative aspect of it. The y axis is the log of k formation. So, that is formation constant the logarithmic value. That means 10 powers are taken by logarithmic. So, that becomes the 3 means 10 power 3, 10 power 6, 10 power 9, 10 power 12, and log k will become 3, 6, 9 and 12, and you take these ligands and add these ions, and all of these are taken as a divalent ions. So, Ba2 plus Sr2 plus, not the Ba atom, Sr atom, calcium atom is the ions. Now, if you add this one and you will form some kind of a complex. So, take oxygen based, the black one here, you start from here as you go from barium to strontium to calcium to magnesium to manganese, etc., etc. It is going and increasing to the maximum at copper and decreases. Now, if you take ethylene diamond nitrogen ligand, it is starting from somewhere much lower than this and then increasing here. And if I take the one nitrogen ligand, other oxygen ligand combined. So, as you can see in all the cases, as you go from left to the right, there is an increase in the formation energy or the formation constant in all of these, and it goes to a peak value around copper and then goes down. I will explain you this in a while, but that is true with all this. So, we have taken oxygen based ligand, we have taken the 2 nitrogen ligands, we have taken 1 oxygen, 1 nitrogen, 2 nitrogens and then 1 nitrogen, 1 sulfur. As you go from oxygen is a very hard kind of thing, and when you go to the next one having 1 oxygen, 1 nitrogen, little bit of soft character is introduced. When you go to the both nitrogens, little more soft character than the oxygen is introduced. When you go to the 1 nitrogen and 1 sulfur, see here 1 sulfur and 1 nitrogen and then much more soft character. so that as the soft character is increased, that is the formation constant is gone down, and on this side the formation constant is gone up. You see that. So, these are barium, strontium, calcium, magnesium, and these are manganese, iron, cobalt, nickel. So, therefore, transition metals behave differently because of their d electronic configurations. So, this kind of a stability order is explained by Irving-William, and this is known as the Irving-William series of divalent cation things. And this can be understood from the following kind of a ionic radii plots and the lattice energies, radius versus the hydration energy of this. You see that it is going down as you add 1 electron, 1 electron, 1 electron, etc. Going to the D5 system, again D6 onwards go down, and the minimum that is coming over here. So, therefore, it is based on the electron connectivity in the D system, that is all we can say, and then goes back to this. So, if you do not have this 5 orbitals and filling 1 each, then followed by the second one, you would not have got like this. You would have got this along with this particular the dotted line. The other one is that if there is no spin problems, then you would have got into these ones. So, therefore, this kind of a ionic radii or the lattice energy or hydration energy can explain. So, here lattice energy, as you see, exactly the reverse of this one, and goes down and again reverse. So, the maximum value here obviously in the negative side, minimum value and maximum value, and that is what you are finding in transition metal. So, in the transition metal it is dependent on the d electron filling. So, therefore, you see the kind of a trend that you see here. So, this kind of a trend. Okay. And we talked about the lability, just this gives you a quantification of the lability. Let us look at the top tire here. The top tire, before going to that, let us see the scale. The scale center point is 10 power 0. As you go right side, 10 power 2, 10 power 4, 10 power 6, 10 power 8, 10 power 10. What is this? This is rate. Rate is what? Per second. So, rate is per second. So, this is a value per second. So, how do we understand? As I told you earlier, you take, let us say, an aqua complex, put into a D2O and see how the D2O is exchanging with the water, or put into a O18 water and see how the O18 is exchanging with the metal center. So, if you look at the alkali ions, they are all having very high rate of exchange, and you take alkaline earth ions, divalent ions, they have a little bit lower. Then you look at some of the trivalents, etc., they have much lower. So, as the charge increasing, their lability is getting decreased as you go from here to here to here, and as you go to this particular within the group as you go from lithium to sodium to potassium to rubidium to cesium, the rate of exchange is increasing. So, what is changing? Not the charge. What is changing? It is the size. So, as the size increases and the charge remains the same, that you have an increase in rate of exchange. So, in other words, in any of the group, as you go from top to the bottom, the size obviously is increasing, the charge is kept maintained constant. So, if you maintain the same charge and the size as you go down the group, then you have an increase in the rate of exchange of the reaction. That similarly, you can see magnesium, calcium, strontium, barium, etc. You can see that again in the alkaline earth ions, again the change will explain the same kind of a rate of exchange. So, now coming to some transition metal ions here, you can see some of the ions are on this side, that means 10 power minus 2, minus 4, minus 6, minus 8, minus 10. This is not plus, and this side is the plus one. So, you can see that some of the ions which are there here, this is the chromium 3 plus, and if you look at the chromium 2 plus, the chromium 2 plus is somewhere here. So, huge difference between chromium 2 plus and chromium 2 plus. You see cobalt 2 plus here and cobalt 3 plus is not shown here, but it will be somewhere in this range, this region. So, therefore, we know that the chromium 3 is a very inert, chromium 2 is very labile. Similarly, iron 2, iron 3, okay, iron 2 is somewhere here, iron 3 is somewhere here. So, very close to the 10 power 2 and this is very close to the 10 power 6 or 7, there is about 10 power 4 difference between iron 2 and iron 3. So, that is why iron 2 is labile and iron 3 is inert. Cobalt 2 is labile, cobalt 3 is inert. Chromium 2 is labile, chromium 3 is inert. Okay. So, all of these. So, you can see that how do you quantify the lability of the complexes. So, how do we quantify the lability of the complex? How do we quantify the stability of the complex? Stability of the complex is quantified by delta G is minus NFE. So, the greater the minus value of the delta G naught, this you take it as delta G naught minus NFE naught. So, therefore, if it goes by this more and more negative, then it is more and more more feasible, more and more stable kind of thing, as you know from the thermodynamic. From the kinetic lability, that is this can be quantified from the crystal field stabilization energy of the reactant minus the crystal field stabilization of the activated complex, and this will give a measure. If this value is positive, it is labile, more positive, more labile, less positive, less labile, but if it is negative, it is inert. So, the opposite to labile is inert. So, labile very fast exchange, inert is very slow exchange or no exchange kind of thing. So, labile and inert are the two terms which you use for kinetics, and the feasible, non-feasible are the terms which you use for the thermodynamics. So, thermodynamic aspects of it and kinetic aspects of it too. Let us look at this particular table for a while. This particular table is given for different D configurations, D0, D1, D2, D3, etc., etc., and it is also given for different spin states as well as the coordination numbers. So, there are 3 parameters: spin state, coordination number and the D configuration. There are 3. It is a kind of a 3-dimensional plot kind of thing. So, if you take the coordination number 5, you see these are the plus values, that means they are labile, and this is a minus value, that means inert, and this is labile. If you see the same high spin with the coordination number 7, these are labile and this is inert. So, similarly, you can gauge which are the labile, which are the so almost all D1, D2 for all the low spin, high spin 5 and 7, they are all labile, and you go to the D3, they are all inert both for the high spin and low spin, and then D4 is again labile only for 5 coordination, but inert for the other one. So, it is not only dependent on the number of electrons present in the D, it also depends upon the number of coordination number as well as the spin state of it. So, continuing to the same thing to D6, D7, D8, D9, etc., you can see that D6, D7 for the high spin, there these and high spin for these coordination number 5, coordination number 7, both of these are labile. But when you go to the other part, that is the low spin part, for the 5 and the 7, they are different. So, that means because the electronic configuration is different. Dn is same, but the electronic configuration is different. So, compared to Dn, you need to give importance to the electronic configuration as well, and the coordination number. So, all these are important. So, for when it comes to the D8, all of them are inert, all of them are inert. We come to the D7, the 5 coordination, 7 coordination high spin are labile, and 5 coordination low spin is also labile, but low spin of the 7 coordination is again inert. So, therefore, you can see the inert and the lability is explained by the difference in the crystal field stabilization energy difference between the reactant and the activated complex. I hope you just read a bit from the known coordination chemistry things to make yourself familiar with this. And let us look at this one. This will explain you the kind of a thing labile, and this is fast because this can be exchanged very easily, and this is again labile and fast, this can be exchanged very easily too, and these are some of the things. So what we need to learn at the end is that in this particular class, let us take metal ion and water bonded to metal ion can polarize the OH bond and give H plus, and this depends on the what kind of a metal ion you have. If you have a calcium 13.4 pKa, manganese 11.1, copper 10.7, zinc 10.0. So, from 14 pKa it goes to 10 pKa, that means it becomes much more labile and can push the proton out. Similarly, an imidazole bound one in the cobalt, nickel and copper. So, this means then when some of the ligands are bound to the metal ion, their polarization of the OH bond varies, and the stronger Lewis acid will polarize better, and that can become instead of OH2 as OH, instead of NH2 as NH. So, such kind of species are dominant during the reactivity, and I will explain when it comes to there, but at that time you should keep in mind the pKa. So, with this kind of thing I will try to close for the coordination chemistry perspectives required for this particular course. And then in the next class I will talk to you about what kind of techniques are used for the gauging the inorganic ions and elements in the biological system. So, therefore, please sort of revise your coordination chemistry abilities using these as a background and going through the some of the very simple textbooks you can look at, and then try to make yourself familiarize with this. Thank you very much.